photoelectric effect. So this is for level 3 modern physics, which is assessed internally in level 3 physics, but is also included in scholarship concepts at the end of the year. Alright, so the first thing I'm going to be looking at is the wave-particle duality theory. So nobody knows what light actually is. It's because light was commonly believed to be behaving like a wave, except that doesn't really require a medium to travel through, unlike sound, which needs a medium to travel through, which is soundness of the wave. Alright, the experiment that showed the wave properties of light is in Young's double slit experiment, so we should have learned about the Young's double slit experiment in our wave standard for level 3 waves. So this occurs when monochromatic light passes through two narrow slits and an interference pattern of sharp and dull fringes were observed. So we see that waves can actually diffract through these slits and then interfere constructively and destructively. They have your nodal lines and your antinodal lines. So on your nodal lines, you have your destructive interference. It's going to form the dull fringes, and on the antinodal lines, it's going to be constructive interference, and you're going to get a bright fringe. So that's how you form the interference pattern. Particles, on the other hand, would pass through the slits in a direct path and not interfere. So if wave were a particle that would pass directly through the slits, there will be no interference, and therefore this interference pattern of bright, dull, alternating bright and dull fringes would not be observed. However, in 1887, Heinrich Hertz discovered the photoelectric effect. So the photoelectric effect is a experiment that showed that wave can also behave like a particle. So light behaves like a wave is shown in the Young's double slit experiment, and light behaving like a particle is shown in the photoelectric effect. Alright, so the experiment or the photoelectric effect occurs when light is incident onto a surface, and it's usually metals, and this light can actually eject electrons off the surface of the metal. This is actually a means of producing electricity, so this is actually used in the solar panels. So it was found that electrons absorb energy from the light, more specifically the photons that light has, which would be able to eject the electrons off the metal. It was found that the frequency of the light and the intensity had unexpected effects on the ejected electrons. So some observations were made. Okay, so here are a list of observations that were made during the photoelectric effect. So the first observation is that the light was able to eject electrons only if the specific frequency threshold is reached, and this is called the threshold frequency. So only light of a specific frequency and higher than that specific frequency can eject electrons. Any light below this threshold frequency was not able to eject any electrons. Number 2, if the light was below the threshold frequency, no electrons were ejected regardless of the length of the time the light was exposed to a metal. So if the light is below this specific threshold frequency, then no matter how long this light was incident onto the metal, no electrons can be ejected. Number 3, if the light is below the threshold frequency and the intensity was increased, still no electrons can be ejected, and that's even no matter how long the light was incident onto the metal. And number 4, if the light was above the threshold frequency and the intensity is increased, more electrons are ejected per unit time, so more electrons are ejected at once, but the maximum kinetic energy of these electrons remains the same. Alright, number 5, energy from a photon can only be absorbed by one particular electron, so therefore one electron can absorb energy from one photon. Number 6, each metal has a different threshold frequency. So if I had a silver metal and a zinc metal, the threshold frequency that's needed to eject electrons will be different for each of these metals. Number 7, not all electrons were ejected with the maximum EK. So some of the electrons were ejected with the maximum EK, but some electrons were not ejected at this maximum EK, at this maximum kinetic energy, at this maximum speed. So some of these electrons were actually having a lower speed. Okay, so not all electrons were ejected with the maximum kinetic energy. And that's assuming that the frequency of the light is above the threshold frequency, so electrons can be ejected in the first place. Right, so why the particle model explains the photoelectric effect? The particle model explains the photoelectric effect because particle model states that light contains massless particles called photons, which have a specific energy which is dependent only on the frequency of the light. That is actually E equals to hf, where h is Planck's constant and f is the frequency of the light. So the experiment shows the electrons cannot be emitted if the frequency of the light was below the threshold frequency. The particle model explains this because electrons can only absorb energy from one photon at a time, meaning that the energy of the photon, of that specific photon, has to be enough to eject that electron. So only the energy of one photon can be used at once to eject any electron from the surface of the metal. So therefore, only light higher than the threshold frequency can actually eject electrons, because E equals to hf. If I have a specific frequency, then each of the photons would have enough energy to eject a specific electron. So if light were a wave, energy would be continuously absorbed over time and leading to the electron being ejected. So if light were a wave, so the electrons can continuously absorb electrons over time, meaning that I can have some frequency light incident on the metal, and after some time electrons will begin to be ejected. However, as we explained, the observation was that no electrons were ejected no matter how long the light was incident on the surface of the metal. Increasing the intensity of the light did not increase the maximum kinetic energy of the electrons, nor did it allow light below the threshold frequency to emit electrons. The intensity of the light allowed more electrons to be emitted per unit of time. The particle model explains this because increasing the intensity means more photons are incident on the metal per unit of time. But since E equals to hf, E is only dependent on the frequency of the light, the energy of the photons remained the same. Therefore, the maximum kinetic energy of these electrons were not affected, and only affected the amount of photons that were incident on the metal per unit of time. Therefore, more electrons can be ejected at once. Alright, so if light were a wave, then increasing the intensity would increase the energy, and therefore the electrons would be ejected with a higher amount of kinetic energy. However, the observations were that was not the case. Right, so the work function. So the work function is defined as the minimum amount of energy required to eject an electron from the metal. So each metal, like I mentioned before, has a different work function. So if I had a silver metal and a zinc metal, the work function of the silver metal would be different to the work function of that zinc metal, okay? Okay, so the work function of the metals represented mathematically by phi, which is the circle with a line through it. Just remember it that way. Okay, so work function depends on the physical properties of the metal and a specific setup on the situation. Therefore, modifications to the surface of the metal, and the work function will be different for each type of metal. The work function is the minimum amount of energy needed to emit electrons, and hence the threshold frequency is the minimum frequency needed to emit electrons. Hence, the energy of the photons of the light of threshold frequency is corresponding to the minimum energy needed to emit electrons, and hence the work function of that particular metal. So therefore, we can actually come up with a formula for our work function for a metal, and that will be simply the work function is equal to Planck's constant times the threshold frequency. And that's because the threshold frequency is the minimum frequency needed to eject electrons, and that corresponds to the minimum amount of energy needed to eject electrons, which is the work function of that metal. Okay, energy of a photon and work function. So electrons can only be ejected from the metal if the energy of the photon is greater than the work function. If the energy is equal to the work function, energy will be absorbed by the electron so that the electron can approach onto the surface of the metal. However, because all the energy was used to move the electron to the surface of the metal, there will be no more energy left to be converted into kinetic energy to allow the electron to move away from the metal. Because there's no kinetic energy allowing the electron to move away from the metal, therefore it's going to fall back to the surface of the metal, and therefore it's actually not ejected. So if we have light incident on the electron, it's going to be brought to the surface. However, there are no kinetic energy left for the electron to move away, hence it falls back down to the surface of the metal. Case number 2 is if the energy of the photon is less than the work function, electrons won't be ejected and they won't have enough energy to reach the surface of the metal, and they will obviously fall back onto the metal and not be ejected. So in this case, we have the light incident with a photon-specific energy. As seen, the electron does not have enough energy to reach the surface of the metal, nor does it have any energy to be ejected away from the metal. So as we see here, the electrons are not ejected. If the electrons of the photon, if the energy of the photon is greater than the work function, electrons will reach the surface of the metal and they will have enough kinetic energy to move away. So in this case, some the energy is absorbed by the electron. Some of that energy is going to be used to move the electron to the surface of the metal, but because there's more energy left over, that energy is going to be converted into kinetic energy, which allows the electron to move away from the metal, and this means that the electron has been ejected from that metal and will not fall back onto the metal. Alright, so the equation for maximum kinetic energy. Since the work function is defined as the minimum amount of energy needed to eject the electron from the surface of the metal, the energy that is left is converted into kinetic energy, which is also the maximum kinetic energy. So we know energy of a photon equals to Planck's constant times its frequency, times the frequency of the light, and the work function is represented by the Greek letter phi. And we know that the maximum kinetic energy will be equal to the energy of the photon, and some of that energy will be used to bring the electron to the surface of the metal, which is the work function of that metal. So the kinetic energy that's left over would be hf minus phi, and that's equal to, and that's actually, this equation is in the form of y equals to mx plus c, so you can see that this is actually a linear graph. So this will be what the linear graph looks like. We have ek max on our y-axis, and we have our frequency on our x-axis. So in this case, our x-intercept is the threshold frequency, because that is the frequency that allows the electrons to have no kinetic energy. So as we can see here, that is the x-intercept. That's the threshold frequency of that specific metal. And we know the y-intercept is when the frequency is 0, so that's when no light is incident onto the metal. And the gradient, it would be Planck's constant, which is h. So that's our gradient. Okay, so here's a practice question. So determine the maximum stopping velocity for electrons emitted from the surface of sodium metal when it is incident with light of 380 nanometers. And question B, will all electrons emitted have this velocity? Explain. Alright, so have a go at this question. So pause the video and give this question a try. And when you're ready, keep watching the video to find out the answer. Oh yeah, don't forget, okay, I did forget about the work function of sodium is 2.3 electron volts. Apologize for that. Okay, so work function of sodium is 2.3 electron volts. Apologize. So now you can try to do the question, and now when you're ready, you can keep watching the video to find out the answer. Right, so for this question, okay, we need to first determine the amount of energy that each photon in the light has. So because we're given the wavelength of the light, we need to use V equals to F lambda to determine the frequency, and E equals to HF to determine the energy of each photon. So we have V equals to F lambda, and we can actually find our frequency, which is equal to 7.895 times 10 to the power 14 hertz. We know that the energy of a photon is equal to the Planck's constant times the frequency of the light, and therefore we will come that the energy of the photon is equal to 5.234 times 10 to the power of negative 19 joules. Alright, so now we have our total energy of the photon, and we have our work function. Okay, so they're in different units. So work function is given in electron volts, and the energy is given in joules. So in this case, we need to convert the joules into electron volts in order to subtract. Okay. So this is step 2. Find the maximum EK by subtracting the work function from the middle of the energy of the photon, because the work function is the amount of energy needed to bring the electron to the surface, and any energy left over after that will be converted into kinetic energy. So we need to convert to electron volts if needed. So in this case, we do need to convert to electron volts because the work function of sodium is given in electron volts. 1 electron volt we know is equal to 1.6 times 10 to the power of negative 19 joules. Therefore, if we convert 5.234 times 10 to the power of negative 19 joules, so you just divide by 1.6 times 10 to the power of negative 19, you will get 3.271 electron volts. So the maximum EK is equal to the difference between the energy of the photon and the work function. And in this case, we'll get 0.971 electron volts. And if we convert that back into kinetic energy, we'll get 1.554 times 10 to the power of negative 19 joules. And finally, we can actually calculate the velocity of the electron using half mv squared. So in this case, EK equals to half mv squared. We know that the kinetic energy we just calculated is the maximum kinetic energy. So we calculate the maximum, just the maximum velocity of the electron. So we can actually find the velocity because we know the mass of the electron is 9.11 times 10 to the power of negative 31 kilograms. And we should find that our velocity comes to be 5.84 times 10 to the power of 5 meters per second. And that's our final answer. Okay, so for question B, it asks us whether all electrons are ejected at 5.84 times 10 to the power of 5 meters per second, and the answer is no, not all electrons are emitted at this velocity. This is because the work function is the minimum amount of energy required to emit the electron. So this is the electron that requires the least amount of work to be done in order to bring it to the surface of the metal, and hence it will have the greatest amount of kinetic energy left over in order to be emitted. So in reality, some electrons will be having a stronger attraction to the metal nuclei, the positively charged metal nuclei, and hence they may require more energy than the work function in order to be brought to the surface of the metal. And therefore there will be less kinetic energy that is left over for it to be emitted from the surface of the metal. So therefore, in reality, some electrons will be emitted at speeds lower than the speed just calculated, and this is because each electron requires different amount of energies to be ejected, and since the incident energy of the photon stays the same, because the frequency of the light stays the same, there is variation in the kinetic energy and hence velocity of the electron. So different electrons will be ejected at different velocities. Alright, so the maximum kinetic energy of the emitted electrons is directly proportional to the difference between the frequency of the light and the threshold frequency of that particular metal. Explain why this is the case. Alright, so have a go at this question, and when you're ready, keep watching the video to find out the answer. Alright, so first we should start out with our definition. So the threshold frequency is defined as the minimum frequency that is required in order for electrons to be emitted, and the work function is defined as the minimum energy required for the electron to be emitted from the metal. So therefore, the threshold frequency is corresponding to the work function. So the threshold frequency, the energy of the photon of the threshold frequency is equal to the work function that's required to bring the electron to the surface of the metal. So therefore E equals to hf. The work function is simply dependent on the threshold frequency as h is a constant. Since the maximum kinetic energy of a photon depends on the difference between the energy of the photon and the work function, so maximum Ek equals to the energy of the photon minus the amount of energy needed to bring it to the surface of the metal. And the energy of the photon is proportional to the frequency. So we know energy of photon proportional to frequency because h is a constant. Planck's constant is 6.63 times 10 to the power negative 34. That is a constant. And the work function is proportional to the threshold frequency. Therefore, the kinetic energy must be proportional to the difference in frequency. So we know the work function is proportional to the threshold frequency. That's because h is a constant, and that the threshold frequency is the energy of the photon of threshold frequency light is corresponding to the work function. That's the energy required to bring the photon to the surface of the metal for a particular metal. So remember that each metal will have a different work function, and therefore each metal will have a different threshold frequency. So therefore, because work function proportional to the threshold frequency, and the kinetic energy is equal to the difference of the energy of the photon and the work function. Therefore, the kinetic energy must be proportional to the difference in the frequencies. And we actually can have a mathematical proof. So we know that the work function is equal to the threshold frequency times Planck's constant. And therefore, we know that the maximum Ek, that is equal to the energy of the photon minus the work function, which therefore equals to hf, the frequency of the light, minus h times the threshold frequency. And we can actually factor out the common multiplier, which is h. So the maximum Ek equals to h times the difference of the frequencies, and because h is a constant, we can say that Ek is proportional to f minus to the frequency minus the threshold frequency, which is what the question was required. Okay. And that's it for part 1 of the photoelectric effect. I hope you enjoyed this video, and if you did, please drop me a like and leave a comment down below. And thank you for watching the video. See you next time. Thank you. Bye.